Alrighty, you guys, let's do a problem that is kind of like the sequel to the previous problem we did, but more correctly, I guess it would be just the other form. Its final form, if you want to call it that way. This one involves what we call numerical iteration. It's just going to be a hoot, but it's actually a little bit simpler in its own way. So anyway, enough prognosticating from me. Let's get going. All right. So the problem says this. It says the satellite from problem 1 is now at perigee of its orbit. Where will it be in 12 hours? Okay. First things first. What have you been given here? Ayo, given a time of flight. We're going to have to convert that to seconds. So let's multiply by 3,600 seconds per hour. That'll give us a time of flight of... We need it in seconds, right? That's how it'll be able to be calculated. 43,200 seconds. Okay, great. Now, true anomaly initial, it says, is perigee. So let's draw our little picture as always. Oh man. Worst ellipse I've drawn so far. Okay, it says I'm right out here. You know what? I'm actually just going to try and do it a little better. Excellence in all my potatoes. Excellence in all my... Oh, there we go. Geez, that's so much better. All right, so there's Earth. It says that the satellite, it's a little bit better, is here at perigee for the problem starting off. So it's 0 degrees. Okay, remember, for our housekeeping step, we're going to do the same thing as the previous problem. As far as I want my true anomaly initial in radians. Well, 0 is 0, right? Even if I multiply by our conversion factor, it's also 0 radians. Now, I want to show you a trick and then prove that it's right. So here's what I'm going to do. Here's the trick. Hooray! If your true anomaly initial is 0, that means that your eccentric anomaly initial and mean anomaly initial are also 0. Why is that? Okay, well, let's jump over to our Excel sheet. So I'm just going to swing around our lines here a little bit. There they go. Oh, they're swinging past perigee. And then here it is swinging past apogee. Let's swing back over to perigee again. So as you guys saw, at perigee and apogee, those 3 lines are all overlapped on top of each other. Well, what is perigee? Perigee is 0 radians. So that means if the satellite's at perigee, it basically chains eccentric anomaly initial and mean anomaly initial to also be 0. Same thing. Let's run it over all the way to apogee. The lines are lined up on apogee 2. That means that eccentric anomaly initial and mean anomaly initial are chained to pi, right? If true anomaly is pi. So let me finish writing out that rule. True anomaly final. Oops, sorry. Actually, shouldn't even use an initial here because really it just means this could be true for final or initial. Basically, if true anomaly is 0, that means the eccentric anomaly and mean anomaly for that time are also 0. For same thing for pi. That's what I was trying to get at. That means that eccentric anomaly and mean anomaly are also pi. Of course, out of habit, I put degrees there. Shouldn't have done. Okay, so if true anomaly is 0, that means it basically chains eccentric anomaly and mean anomaly to also be 0. If your true anomaly is pi, E and M have to follow it and also be pi. Yeah, so here you can see as we swing around from perigee out to apogee. All of the three brothers, if you will, the true anomaly, eccentric anomaly, and mean anomaly, are all in that upper half plane. And then as soon as we pass apogee, well, first let's look at apogee. At apogee, all three brothers are stacked on top, right? They're all the same value at pi. And then as they swing past apogee, the three brothers, true anomaly, eccentric anomaly, and mean anomaly, are on the lower half plane. So this is why if you're, for example, your true anomaly initial is up in that upper half plane, and then true anomaly, true anomaly initial is up in the upper half plane and eccentric anomaly, the equation tells you it's in the bottom plane, can't be, right? All these lines are always in the same half plane. So that's what this little demo is meant to show you. Okay. So I don't want you to take that for granted. I want to prove it. So let's see here. Let's use our cosine of eccentric anomaly initial. Let's find it. Let's prove ourselves this trick really works. Okay, so remembering that I get this from my equation sheet, right? The cosine of eccentric anomaly is that gobbledygook. Well, let's see. Actually, let me not put an equal sign here. Let's go ahead and take our eccentric anomaly initial and isolate it. Let's see here. 1 plus e cosine initial. Okay. Inverse cosine. Oh, we're going to have to get a little bit tiny over here. ER eccentricity is still 0.2 plus cosine of, remember, our true anomaly initial is 0. Cosine of 0 over 1 plus 0.2 cosine of 0. Okay, so what does this come out to be? Inverse cosine of 0.2 plus 1. Do you guys buy that the cosine of 0 is 1? Plus 1 plus 0.2 cosine. Oh, well, cosine of 0. I'm just going to go ahead and replace it with 1. So what does this end up being, I should say? It ends up being 1.2 over 1.2 equals the inverse cosine of 1. In case you're curious, that works out to 0. Okay, so that means our eccentric anomaly initial is 0. Just like the trick said, so it must be right. Well, let's see if it works for mean anomaly initial too. I'm going to grab that right off my equation sheet here. Mean anomaly is eccentric anomaly initial minus e sine eccentric anomaly initial. That means 0 minus 0.2 sine of 0. What's the sine of 0? 0. This means this is 0.2 times 0. 0 minus 0 will all be. The trick works like magic. So what I'm trying to tell you is on a GR, if you're trying to save time, make sure to check if true anomaly initial is 0 or pi, because that will chain eccentric anomaly initial, mean anomaly initial to also be either 0 or pi, respectively. And you don't have to go through this process. You can trust the rule. We just proved it. QED, right? Thus, it is proven. So in our case, we proved to ourselves the trick works. Okay. Well, that's great and all, Major Cunningham, but what's the overall process for this problem here? Well, we're going to take true anomaly initial. Oops. And you might remember the kind of little chain process I drew here. We use true anomaly initial to get eccentric anomaly initial, then mean anomaly initial. We used that to get our time of flight because we did true anomaly final, right? from before, but instead of two basically ingredients going into time of flight, we have time of flight, and we're just going to keep walking it back to get our mean anomaly final, our eccentric anomaly final, and our true anomaly final. Because really it says, where will it be in a certain amount of time? It's asking for, where will it be? Means it's asking for true anomaly final. Okay. So let me come back to this, because we just proved that if true anomaly initial is 0, or pi, right? If it's 0, then that means E and M are also going to be 0. And if it's pi, they're also going to be pi. But the problem gave us true anomaly initial of 0. Great. That means we did this step. True anomaly initial was given. Because it's 0, that means E sub I is 0. And mean anomaly initial, M sub I, is 0. All right, now let's plug that into time of flight. So if I was going to kind of put some steps on this, you're gonna do this process here. Step 2 is going to be to find time of flight, and then step 3 is going to be to go through this process. Bingo, bango, bongo. Okay, so we've done step 1. That was all this. Now let's do step 2. Let's get that time of flight. What say you? I say yes. Okay, we're going to just drag our true anomaly, or sorry, our time of flight equation off the equation sheet. Anomaly final. Let's see. I should amend my step. Actually, what I want to say is that step 2 here is using time of flight to get mean anomaly final. So I don't want to make this too much of a checklist-based process, but these are, kind of recipes. So using time of flight to get mean anomaly final. That's step 2. Okay. Anyway, so mean anomaly final. Let's drag it off the equation sheet. Minus mean anomaly initial. I'm using this one right here for you guys following along at home. Is mean anomaly, or sorry, mean motion times time of flight minus this pesky 2 pi k thing. We're actually going to use it in a different way this time around. It's kind of cool. So let's plug and chug as much as we can. So first things first, we're going to have to do the process of finding what mean motion is. It's mu over a cubed. We're just using that same equation as before from the equation sheet. Let's plug and chug. Percent major axis is still 18.5. So that's convenient. So I guess I could take the mean motion from the previous problem and not recalculate, but I'm just going to recalculate. Square root of that bad boy. 2.5091 times 10 to the negative 4th radians per second. Okay, great. Here's what I'm going to do. I'm going to leave this 2k pi thing alone for a second. And this is where you really start to see some of the fudge factor and the imprecision of this process. Kepler gave us our best approximation, right? We're using 2 circles interlaced to try and find out what's going on with an ellipse. That doesn't mean it's perfect. It doesn't mean it follows the same very linear, perfect mathematical processes as before. Like, would I ever tell you to leave out, randomly leave out a variable in any of these other equations in the equation sheet? No, I wouldn't. But for this, we are trying to find where the satellite's going to be in a certain amount of hours, which is a very real-world practical problem. I'm going to have to use some fudge factor. So anyway, step 2.1, if you want to call it that, leave that alone for now, and just find mean anomaly final, like this. We'll plug and chug, and we'll use 2 pi k in a second. Let's plug. We found that mean anomaly initial was 0 from before, and now let's multiply 2.05091 times 10 to the negative 4th times our time of flight in seconds. That's why I converted it in seconds up here. That's in radians per second, and that's in seconds. Okay. Okay, awesome. This gives us some amount of radians. It gives us 10.8391. Again, carrying all those digits. Radians. Let's think back to the previous problem. If you remember, I had drawn you my elliptical orbit with Earth right here-ish. And we have to do this half plane check thing. If you remember, if we divide the orbit in half like this, you know, your true anomaly initial. Let me try to make that a little more of a dotted line. Yeah, okay. True anomaly would be 0 right here. True anomaly would be pi over here at apogee. So remember, if I get true anomaly initial to be in the upper quadrant, I want it to be in that upper quadrant for E and M. Same thing if it's in the bottom quadrant. So I'm trying to do my art class shading in a different direction here. That's why computers exist, so I don't have to draw. But not a bad thing. Anyway, so remember, yeah, if true anomaly initial is between 0 and pi, that means its friends E and M have to also be in this upper quadrant between 0 and pi. Same thing if it's, you know, between pi and 2 pi. But here's something interesting. A full orbit worth is 2 pi of true anomaly. What is 2 pi? 2 pi is about 6.28ish, right? So are you telling me that this mean anomaly final is spitting out something that's more than 1 orbit's worth of true anomaly, basically, or sorry, of rotation, I should say? Because 2 pi of rotation for true anomaly, for eccentric anomaly, and mean anomaly is still 1 orbit's worth. And this sucker, this mean anomaly final, how dare it, it gave us 10 point something something. So that's far more than just 1 orbit's worth of rotation. That doesn't do us much good. What we have to do is get this number. This is another kind of a fudge factor thing. I have to get this number under 6.28 because I'm really just concerned about 1 orbit's worth of rotation, or less than 1 orbit's worth of rotation. So I'm going to subtract 2 pi's from this number until I get under 2 pi. And if that makes your head hurt, not to worry. It's a little bit of a mind game. So I'm just going to say 2 pi so I don't carry a rounding error. And then you can just plug that direct into your calculator. This gives us 4.55596. 55596 radians. We have example problems where mean anomaly final spits out something that's almost like 30 radians. So you have to keep subtracting 2 pi and keep subtracting 2 pi until you get under 2 pi. I know it's kind of weird, but you want the final number to be between 0 and 2 pi because that's just 1 orbit's worth of rotation. The mean anomaly final equation is very eager to serve you. It's very happy, and it says, you want to know about the rotation? I'm going to give you all the rotations. I'm going to give you all the rotations this thing's ever done in the course of the problem. And you're like, okay, chill, mean anomaly final. I appreciate you doing that, but I'm only really interested in 1 orbit's worth of rotation. And it's like, oh, okay, well, I guess you'll have to subtract 2 pi's from me until I finally get under 2 pi worth of rotation. You're like, okay, I kind of wish you would be a little more chill, mean anomaly final, but that's just how you are. Very eager little variable. Okay. All right, all joking aside, we only had to subtract 2 pi, 1 iteration, 1k, right? 1 pi, 2 pi rotation off of mean anomaly final to get under 2 pi because 4.5596 is between 0 and 2 pi, which is 6.28. Excelente. Let's go to a new sheet of paper. Actually, I'll put this over here. Alrighty. So now let's go back to our little process. We've gone all the way through using time of flight to get mean anomaly final. This is where we're going to have to do this thing called iteration. We're now at step 3 using mean anomaly final to get eccentric anomaly final. Okay. Let me put that up there from right meow. So now we're on step 3. I want to get eccentric anomaly final. so that I can eventually get true anomaly final, right? And that's the holy grail of this problem. I want to get true anomaly final. So eccentric anomaly final is a step on that process. So I'm going to use and then manipulate this equation right here, m equals e minus e sine e, little e, sine big E. But I'm going to switch it around like so. I'm going to try and isolate eccentric anomaly final. But you're going to find this kind of to be an interesting issue here, because I can get eccentric anomaly final on its own, but I can't get it out of this e sine big E equation. Okay, one crisis at a time. Let's see. Mean anomaly final. I rearranged the equation as much as I could. Do you guys understand or buy the fact that I'm telling you that I can't get eccentric anomaly final on its own out of this sine? Because if I were to try and get rid of this sine function, I'd have to take inverse sine of everything else, and that's fine. That would give me eccentric anomaly final on its own over here. But then I'd have inverse sine of eccentric anomaly final over here. This equation is what we call transcendental in eccentric anomaly final. So transcendental in the variable of E sub f. Means you can't get it alone. Cannot find a way to get it alone. That's okay. We've got a solution for that. So first thing you're going to do, you're going to use mean anomaly final right here, and also use mean anomaly final as your first guess. For eccentric anomaly final. Here's how this is going to work out. From before, we found that our mean anomaly final was this long 4.55596. So for our first guess, or first try, if you want to put it like that, eccentric anomaly final is this mean anomaly final plus E sine mean anomaly final, right? It's our first guess. So what's that going to look like numbers-wise? Well, it's going to look like this. 5, 5, 5, 9, 6 plus eccentricity, which is 0.2, times the sine of our guess, which is 4.55596. Well, what does that spit out? Let us see. Gives us 4.3, 3, 5, 8, 4. Okay. That's fine. Let's do our second try, because we're not there yet. I'm going to show you why. Okay, so I'm going to label EF1 as our first try. EF2, our second try, is going to be mean anomaly final. And here's where it gets a little weird, plus E sine, not original mean anomaly final. We're going to use E sine of what we got for the previous problem, or for the previous iteration of E. What's that going to give us? Let's see, 4.55596 plus 0.2, fine, of what we got from the previous. Ooh, that gives us 4.3684. You might say, okay, can you just stop for a second, Major Cunningham? Why did you go past this first iteration of eccentric anomaly final? I'll tell you why. We want our answer for eccentric anomaly final to converge. This term converge means stop changing significantly. Stop changing much. How much? How much is enough? We decide. Right? We the space operators decide. We the engineers decide. In Astro 310, use a convergence criteria of 0.0001. What on earth is a convergence criteria? Okay. What that's talking about is how precisely do you want your eccentric anomaly final to be? And generally, in Astro 310, unless you're told otherwise, notice how the problem doesn't give us convergence criteria at all. It says, up to you, buddy. Well, it's not really up to you. Use 0.0001. So what that means is I want the tenths, hundredths, thousandths, 10,000th place to stop changing. Okay? And or let me put it this way. All the digits between the tenths need to stay the same, the hundredths need to stay the same, thousandths need to stay the same, and then the 10,000ths needs to stay the same. So let's analyze what we've got here for eccentric anomaly final and eccentric anomaly final step 2, or try number 2. 4 stayed the same, 3 stayed the same, but we jumped up from 5 to 6. So, okay, we haven't hit our convergence criteria yet. 8 and 4 stayed the same, but we don't care about those yet because we can't even get the hundredths to stop changing yet. All right, one crisis at a time. Let's do our third try. I will label that as E sub final 3. So it's still going to be mean anomaly final. Hopefully you start noticing the pattern. Eccentricity, sine of what we got for the previous iteration, 4.3684. Notice I am carrying 4 digits after the decimal. Okay. 4.5559 plus 0.2. Sine of what we got from 4, 4.684. What's that going to give us? Oh. So it gives us 4.37, sorry, 3713. All right, well, let's do our convergence kind of check here. Let's try and write legibly. Always my challenge. 3713. All right, so 4 stayed the same from before. 3 stayed the same, but again, this hundredths digit continues to change. So, fourth try. Now, those of you who are calculator wizards might notice that there's some efficiencies you can do here. You don't have to keep writing this all the way out. And in fact, especially on a GR, I would encourage you not to. If you can do like answer plus 0.2 sine answer, or like, sorry, 4.5596 plus 0.2 sine answer from before, that's generally how you want to speed this up. So I'm going to trust that you know that M sub final is as it was before. You know what? Heck, I'll just write it out. 4.55596 plus, 0.2 sine of what we got from a 4.3713. Okay. Ah, darn. This gives us 4.3674. This is interesting because it popped up and then went back down. So 4.3713. Okay, great. 4.3674. Okay. Yep. looks like that hundredths digit changed again. Back to the drawing board. Now, I want to highlight something to you guys. Just because it won't converge on the first few tries doesn't mean you're doing something wrong. It means you're actually doing something right. And it's just part of the process. First victory. So finally down here on the fifth try, I get 377. So 4 stayed the same, 3 stayed the same, 6 stayed the same. Finally, even now the thousandth stayed the same, 7. Okay, we're almost to our convergence criteria of this 10,000th place not changing. I suspect we only have a couple more tries at the most. Okay, 6th try. .555596 plus 0.2 sine of what we got from before, 3677. Finally, I get 4.3677. 4 stopped changing, 3 stopped changing or stayed the same, 3 stayed the same, 6 stayed the same, 7 stayed the same, 7 stayed the same. Finally, our 0.0001 convergence criteria is met. And I'm just going to underline it because I'm so proud. All right, so our eccentric anomaly final is what we got after the 6th try. Just happened to be when it finally stopped changing. And that's 4.3677. Now, let's think about our half plane check. Mean anomaly final. Whoo, way back in the previous sheet of paper, we found mean anomaly final was 4.55596. We've been using it the whole time. That is between pi, which is 3.14, and 2 pi, which is about 6.28. That means that its brothers, eccentric anomaly final and true anomaly final, have got to also be in this bottom quadrant here, or not wrong word, bottom half plane. Is it? Half plane check. Is eccentric anomaly final of 4.3677 between pi and 2 pi? Yes, it is. So we are good to go. Because pi, which is 3.14, is less than what we got for eccentric anomaly final, which is between 2 pi. That's the half plane check. Okay. Whew. The hard part's over. We just have one more plug and chug to do. No iteration. And I guess I would label this as maybe our 4th step here, if you want to call it that. Just finally using our highly iterated eccentric anomaly final that we really worked hard for. We're going to use it over here to get our true anomaly final. So pulling right off the equation sheet, cosine of true anomaly is equal to cosine of eccentric anomaly minus eccentricity over 1 minus eccentricity times the cosine of eccentric anomaly. Let's plug it in. So I'm going to just isolate true anomaly final is the inverse cosine of all this. So cosine of eccentric anomaly final, which we finally decided was 4.3677 minus 0.2. Be careful with your math here that you don't take the cosine of 4 minus 0.2. Make sure you say cosine of 4.3677, that quantity minus 0.2. That's a common error. Let's finally get this plugged and chugged. Haha. Oh, brother. So we get 2.0988 radians. Half plane check. I have a creeping suspicion. Let's check. Half plane check. So let's see. Both mean anomaly final, eccentric anomaly final are between pi and 2 pi. What about mean anomaly final? Mean anomaly final, unfortunately, is between 0 and pi. Pi is 3.14. Our mean anomaly final and eccentric anomaly final, are between pi and 2 pi. Well, shoot. So that means what we got to do is take and do the half plane check execution here, which is to say we're going to take 2 pi minus what we got for true anomaly final. And that will finally be our answer. Whew. 4.18. 4 radians. That's our true anomaly final. Man, let's think through this real quick. So, way back when, we were given a true anomaly initial, right? So we're at perigee. Same centimeter axis as before. Where will it be in 12 hours? So it's asking where will it be? That means true anomaly final is what they want. And then they pitch you, they softball you a time of flight. We use a similar process to the previous problem. Start off with true anomaly initial, march that all the way forward to mean anomaly initial. We use that in time of flight, to come down here and get mean anomaly final. Then comes the big step 3 of going from mean anomaly final to eccentric anomaly final. That was this whole thing with the iteration. And we have to do our convergence criteria and make sure each answer starts getting closer. You want it to. Of course, we want to do our half plane check at the end to make sure that our half plane of eccentric anomaly final after the iteration is in the same half plane as mean anomaly final. Turned out it was. We used that to finally get true anomaly final, and that spat out something in the wrong half plane. We did our half plane check, and then we did 2 pi minus it to get our final true anomaly in radians. Now, the problem said that was fine, right? It didn't say you had to convert back to degrees. You can if you want to, but this is where we can legitimately stop. Whew. All right, thanks for following along, guys. You hung in there, and I recommend doing some practice with this. And don't forget your trick. Don't forget that if true anomaly is 0, it's going to chain its brother's eccentric anomaly and mean anomaly to be 0. Same for if it's pi. So we proved that in this problem, but you don't have to prove it to yourself if you buy it. I was doing that as a teaching process. So look for that trick. Look for the trick, and you can save yourself some time. Okay, thanks.